for everybody here to remember is that this is an international problem. And the skimming and the chopping and the parsing of reporting stations reminds me of what either Lenin or Stalin said. It's not how many votes are cast, it's who gets to count the votes. And these people are counting the numbers and making it look like they're producing a real record, when in fact one of the things they're doing is eliminating all these sites that have a tendency to be cooler sites. The next speaker is also a person who's become important and prominent in the climate science business because he spent 20 years doing the basic research on all sorts of climate and weather phenomena, but has in recent years become a very articulate and insightful critic of modeling plans. I called him a model, you're my modeler guy, when he said, no, I'm not a modeler guy. And he is definitely a guy who has the modeling issues in hand. So Chip Knappenberger.
I am not a modeling guy. Let's just clear that up right now. I'm an observation guy, and I will use observations to test the models, like Dr. Lindzen called for at lunch today. For the past 20 years or 25 years, I've had the distinct privilege and unique opportunity to work with Patrick Michaels closely on a lot of issues of global climate change. And if you know Pat personally or saw him this morning, you know he's an energetic guy with a lot of different sort of eclectic interests. And working for him demands that I wear many different caps from time to time. Sometimes we're ICCC critic, sometimes we're EPA commentator, sometimes I'm a climate science defender, other times last week we were a climate policy sort of analysts. You saw Chris Horner and Pat this morning showed some of our results that show the new bill proposed by Kerry. And Lieberman isn't going to have any effect on the climate, but it's probably going to have lots of other effects that you might not be so happy about. Today I'm going to describe results, some efforts I've been doing where I'm wearing a hat of climate researcher. It's one that I only get to wear fleetingly, but it's probably the one that I enjoy the most. So I'm going to talk about some original climate research that we're doing with attempting to compare projections from climate models to observations of global average temperature during the short term. And I'm emphasizing the short term here because climate models, if you use them to hindcast, they are tweaked so that they get the observed temperatures right. So we're holding the models to only be using in a projection mode from 2001 onward. But I'll get to that in a minute. I've been helped out a lot with some collaborators on this work. Pat Michaels, who I mentioned before, John Christie, Chad Herman, who we found on Lucia's blog, and Lucia's helping us out with this as well. And interestingly, the last collaborator is James Anand. And James, you might, if you know anything about him, you will see that he normally does not run in the circles of the rest of the names that are on that list. We've been trying to get this work published for some time, and we get rejection after rejection after rejection without any opportunity to respond to our critics. So this is a bit frustrating. So I approached James, who is someone who's typically on the other side of this issue, to see if he would engage me in a constructive conversation about just what it is that's so bothersome about these results. They get rejected all the time. And we had James was very good, we had a very good conversation back and forth, and it turns out that he was a reviewer of one of the papers that got rejected at some point. I did not know this when I was talking to him about it, but again, it was very constructive, and in fact, so constructive that James came on as a collaborator and co-author on this work. So maybe we're winning him over one at a time, but we're working on it. So what we were after here is we often hear people say global warming has stopped, and it has. definitely slowed down depending on what period you look for. And this is interesting, but we want to know, what does it really mean? Because if you compare it against the model average temperature, the guys say, well, that's not a fair comparison because there are natural variability that happens on time scales of years to decades that have impacted the observations, but all those things get averaged out in the model ensemble average. So we wanted to ask the question, okay, what is the model ensemble average, and what is the distribution of short-term trends that are around that average? So we're looking at basically the model average and the model standard deviation for these short period trends. So our goal here is to find out just how unusual the lack of global warming, that global warming has stopped, really is. And here's sort of a little introduction to the problem. Here are some observed temperatures since 1995. The period since then, when people start talking about global warming is stopping or slowing down. This is just the 3 surface data sets. And so the question is that what you see there unusual when you look about them with what models are projecting? So my bottom graph is a collection of 50 different climate model runs for the first 20 years of the 21st century. And so you can see the black line in the middle is the ensemble average, but you can see there's a lot of noise about that average. So the question is, can you find some period of no trend? Here's a 12-year period of no trend since 1998. Does such a thing like that exist somewhere in that bottom graph? And if so, how frequently does it exist in there? That's the question we sought to answer. So to do this, we used the standard global average temperature data sets. We didn't make any value judgments about these data sets. We're just using them as they are. We have 3 surface temperature data sets that we're familiar with, NCDC, the NASA GIST data set, and the Hadley Center data set. And we have 2 observed data sets of lower tropospheric temperatures from satellites. We have John Christie and Roy Spencer's University of Alabama Huntsville data set, and we have the remote sensing system data set that we used. Then we went and collected the model global average temperature projections from 20 different climate models, and we had a total of 50 different individual runs. We limited our analysis to the period of January 2001 to December 2020. This is pure projections from the models. And that first 2 decades of the 21st century, the model output and the model projections are pretty stationary. The trend is linear, and as you saw from my, let's go back this way. You can see the trend is pretty consistent over time, and so is the variability. So that first 2 decades of the 21st century ought to be a pretty fair representation of what's happening during the first part, what's been projected to happen during the first part of this century. We calculated trends through the temperature anomalies, and we looked at trends in length from 5 years. We used monthly data, so it's 60 months all the way out to 15 years. And we compared those to the distribution of model trends. The model were run with the SRES A1B scenario, which is sort of a business as usual scenario that pretty closely matches the observed forcings during the past 10 or 12 years or so. And we've also made the assumption that climate models adequately represent short-term climate weather processes like El Nino, Pacific Decadal Oscillation Index, Atlantic Multi-Decadal Oscillation. Again, I'm not saying that they actually do that, but that's the assumption that we made when we're testing these things. So this is the distribution of 10-year trends, 120 months in length, from the climate models, okay? So we see the mean is somewhere around 0.02 degrees C per year. That's that 0.2 degrees Celsius per decade number that we're supposed to be warming at. But there's a pretty broad range of model projected trends that can be in 10 years of length. So if we look at point number 3, well, point number 2, it's pretty well fit for a normal distribution. Normal distribution pretty much fits those model trends, so we're going to sort of assume normality in these model projections from here on out. And point number 3 is the cumulative probability of a trend that is equal to or less than 0, basically global warming has stopped, is 7.9% in this collection of climate models. And that's sort of represented on the way out on the left-hand side of this of this tail of the distribution. So if you're using the 1 in 20 significance value as being indication of statistically significant differences between observations and models, you see you need to have a trend of 10 years that's a little bit less than 0 before it's statistically different from the model distribution there. So this is the 10-year trend, and like I said before, we looked at trends from 5 to 15 years in length. So I'm going to show you all those results at one time, but instead of showing you a bunch of distributions, these bell-shaped distributions, I'm going to turn them on its side and plot it like this. So if you look at the, let me see if I can explain what this is. Along the bottom is trend length from 5 to 15 years. Along the outside is the actual trend value. And I've also, all those dotted lines are the cumulative probabilities going from very rare at the low end, 1, 2.5, 5% cumulative probability. There's the 50% cumulative probability. And then up here on these high trends of on the order of a degree C per decade, way up here, are very rare. So the 50% cumulative probability is this 0.2 degrees C per decade value that we're familiar with as what the models projected global temperature should do during the first couple decades of the 21st century. And like I showed you before, here's the 7.9% cumulative probability for a 0 trend. I've indicated a 0 trend by this solid horizontal line right there. And so where that solid horizontal line intersects these cumulative probability, you see it's between 5 and 10%, it's actually 7.9%. So a lot of people are interested in what are the chances, how long does global warming have to stop before the models are wrong about it? So what you notice here, I call this sort of a trumpet chart. It's, for short trends, there's a lot more variability, and by the time you get out here to longer trends of 15 years in length, the variability, the shaded region indicates 95% confidence about the mean. You see it gets pretty tight out here at the end. So for a 6-year trend, as global warming has stopped, would be the chance of that happening is 22.6%, which isn't all that particularly uncommon. 7.9% for a 10-year trend. But then when you get out here to 12 and 14 years, it's very rare. It's only a 1% chance that the models, that a global warming would have stopped, a 0 trend would likely to occur in the model projections. So if you're interested in that 1 in 20 value, it turns out to be a trend of about 11 years. So if global warming has stopped for 11 years, that would be a very unusual situation, indicate that the models are a statistically different from the model projections. So I'm showing you surface data. We can create the same distribution patterns using the lower troposphere data. One of the things you're going to notice is that the model projected trends for the lower troposphere are higher. It's 0.25 degrees C per decade. That's that increase of temperature, of warming with altitude that we hear a lot about. But also the variability is greater at that altitude, in that part of the atmosphere. So the width of the trumpet, if you will, is a little bit wider. And so the combination of a higher mean and a wider variability, a larger variability, tends to work their way out so that the probabilities for a 0 trend turn out to be very similar to that we saw at the surface. So it's still about a 7.5% chance that a trend of 10 years in length of a value of 0 was expected by the models. And it also works out to the statistically difference between observations and models works out to about 11 years. So that is just a global warming has stopped a 0 degree projection or 0 degree observed trend. So, but that's not exactly what has occurred. Trends of different lengths have taken on different values. So what I'm going to plot on here now is the the GIST temperature trends for different lengths. These are the actual observed trends ending in December of 2009, which is the data we had when we submitted the paper. So now you can see how, you'll see at some cases out here at 10 or 11 years, which begin just after the big El Nino, so they begin in like 99 and 2000 when we were in a La Nina. There's been warming since then, and you can see that they start to flirt with the mean of the model projections if we're using the GIST data, which is the warmest of all the surface temperature data. I shouldn't say the warmest, the one that's been warming the most during the past decade or so. The Hadley Center data is the surface temperature data set that's been warming the least. And you can see here, this is the 5% cumulative probability, and the gray line is outside the 2.5%. Out here at about 12, 13 years, and even further, you can see that the GIS, the Hadley Center data, the models are having trouble expecting what the Hadley Center is measuring. And the NCDC data is sort of in between those things. But again, it's all way out, if you will, on the left-hand side of the distribution. I'll quickly show you what it looks like for the satellites. That's the Spencer and Christie satellite, and this is the guy's remote sensing system. Again, the satellites are laying out near the low end of this distribution. So if you, the next curve plot I'm going to show you is going to be what the actual percentages are, what the cumulative probability are for all the observed data. And it's a plot that looks like this, and I'll put up the 5%, the 1 in 20% statistical significance. So anything that falls below that dotted line is statistically significantly different. The observations are different from the model expectations. So the models are struggling here, clearly. The best you can say about the models is that, well, they tend to, the observed data tends to fall in this 5 to 20% chance, which 1 in 20 to 1 in 5% chance, which to me is not a sign, I don't have a whole lot of confidence in the models are working very well. And especially when you see them down here below this. This is a sign to me of model failure or something that's heading very close to that. So, to sum up here, the observed trends in the global average temperature record from 5 to 15 years in length lie out the lower tails of the probability distribution as we talked about. Typically between 5 and 20%, which is, to me, doesn't make me very comfortable if in having high confidence in the models. Taken together, our results call into question the consistency between the observed evolution of global temperatures in recent years and the climate model projections. And so global warming has stopped, or at least it's greatly slowed, and this is fast becoming a problem if you're a believer in model projections. So possible sources of this problem include unknown errors with the observed temperature record. As Anthony has just shown us, the temperature record is probably warming too much, which would push things further out in the left, which cause even more problems with the model projections. There could be differences between the A1B forcings and the true forcings, although I'm pretty confident that they're similar to each other. And the bottom three all talk about model problems. It could be that the models do not accurately replicate characteristics of natural variability. That's probably true. It could be that the models are having trouble with transient climate evolution. That's probably true. And the third one, it seems like there could be an overestimation of the climate sensitivity, which we heard about at lunch today, which also is going to be a problem. So taking all those things together, my confidence that the models are giving us good information of how the future global climate, global temperatures are going to evolve is not very high. So since I have my climate researcher hat on, I'll finish with there's still a lot of work to be done here, which is code talk for please send us money and we'll keep working on this. Thank you very much.